I want to talk a little bit about how module import works, and I want to distinguish between the different ways that we might go about importing a module. Now, for those of you who have seen any code that I've written using pandas, you know I'm the person who does from pandas import data frame. If you want to turn your computer off right here and right now because you cannot abide by anything but import pandas as PD, I won't blame you. I do that for a very specific reason. Generally, if I want to show somebody how to go about doing something, I like to show them all the pieces they need up front. Generally, if I want to show you how to do something, I want to keep in mind that maybe some names that I'm pulling from pandas may or may not exist in your version of pandas. So I want you to be able to know right up front, right at the very top, what you're going to need, and to be warned if that doesn't exist because you're on an old version of pandas. And also, aesthetically, maybe I like it, and also, I guess I just like to irritate people by saying from pandas import data frame. And between you and me in practice, it really is not much harder. I mean, I find that I can write pandas code just as quickly as the people who import pandas as PD. But I want to talk about what the distinction might be between these different styles of import and what that means in terms of how import works. I want to start by considering the distinction between early and late binding, which goes beyond the discussion of imports and in fact shows up in all aspects of our work. Here's what I mean by early and late binding. We have two pieces of data, two names that refer to some data. X's refers to some data, Y's refers to some data. Y's is explicitly a copy of X's. Therefore, if I change X's, Y's does not change. It's a copy. It's a snapshot in time. However, if I say Y's equals X's, Y's is now a view of X's. It refers to the same underlying data. So if I change X's, they both change. This is a live view. We're very familiar with the distinction between live views and snapshot views and how they influence our work. There may be some places where we may not be aware of where we might be taking snapshots and we don't intend to, or we're making a decision between a live view or a snapshot view. But especially if we're a NumPy user, we're very familiar with, is this a copy or a view? Is this live or is this a snapshot? By the way, I shouldn't call this a snapshot view. I should call it a live view or a snapshot. Let me show you an example where this might come up that you might not anticipate. If I were designing a class, I could say pass in some data by just passing in a parameter data and assigning self.data equals data. And here, what I can see is if I change data after I pass it into this class, well, it's actually changed in both places. Here, I just have a reference to the underlying data. And because this exists outside of this class in some other scope, other people can change it, and that change will be reflected. Here, I'm saying the data that I'm working on is a live view of whatever you pass in. It is not a copy. Therefore, if you make changes to the live view, I will get the updated version. And of course, the live view versus snapshot makes a lot of sense to us. Sometimes you want to get a snapshot point in time, and sometimes you want to be responsive to any changes that happen throughout the lifetime of that data. Well, if I do an explicit data.copy, well, that's a copy. If I do an unpacking using one of these generalized syntax, that's also a copy. I threw away the outside container. So this is also a copy. If I do a list comprehension, going through these elements and filtering them, even if the filtering doesn't filter them in any meaningful way, that's also a copy. If I do something like list of data, that's also a copy. And so in this second example, what you can see is the change on the outside was not visible on the inside because I took a snapshot. And when I use things like star arguments or star keyword arguments, that also makes a copy, because what you can think is I'm decomposing the collection and then I'm reconstituting it via the star args mechanism. This actually implicitly made a copy of this data. And so changes on the outside are not visible to this class. It implicitly made a copy, even though when you look at the syntax, it might be hard for you to distinguish this from this. One single piece here changed this from, are you a live view or are you a snapshot view? Well, it turns out that there are other implications to this live view or snapshot. One of them is if we want to inject behavior associated with some sort of container type, that might be something that we are prevented from doing with the various ways that we might make copies. For example, if we do self.data equals data, then if this data has some additional behaviors, it's a default dictionary, so it auto-vivifies default values, I preserve that. If I do a data.copy, that's still preserved. If I do this kind of unpacking, it actually gives me a strict dictionary back, so I've thrown away that behavior, which may or may not be what I want to do. If I try to get clever and say, I want to do some sort of filtering and I'll reconstitute the same type using this mechanism, this is unlikely to actually work. The default dictionary takes as its first argument the type, and you'd never know in the arbitrary case what those keyword arguments would be, and so you really can't do this. And one thing you can think is, if I were to make mutations to the data inside this class, those mutations would also be visible on the outside. And so this copy versus slide view is oftentimes, what's the scope of changes? Do I want to be responsive to every change and also be able to make changes external to what I can see, make changes to the outside world, to other people's view of this? And do I want to be responsive to any behaviors that might be passed in? And do I want to maintain those behaviors, or do I want to throw those away? Sometimes you want one, sometimes you want the other. As an aside, I want to briefly talk about equivalence versus identity. Here, we can see two distinct Python lists. They are equivalent, they contain the same entries, but they are not identical. They are distinct lists. And one way we know they aren't identical is if we look at the IDs of them. The unique identifier for X's does not match the unique identifier for Y's because they are distinct objects. So here, our unique identifiers won't match. And if you're in CPython, in a current version of CPython, you can even see these are the pointer locations for that underlying object. You can see these are completely different objects at different parts in memory, which means if I edit one of these, if I edit X's, Y's will not be changed, and they'll no longer be equivalent, and they'll remain as non-identical. If Y's is equal to X's, then Y's and X's are both identical and equivalent, which means if I change X's, well, Y's is just a different name to refer to the same data as X's, and so they change in tandem. It is not the case that you're either equivalent and identical, or maybe equivalent and not identical. All four possibilities, equivalent and identical, equivalent, not identical, not identical, equivalent, not identical, not equivalent, all four are possible because it's possible for an object to be identical to itself. You know, something's always identical to itself, but not equivalent to itself. You know, any arbitrary Python object can define EQ and return false from this. So it's possible to be identical, but not equivalent because of some behavior in EQ. And a canonical example of this is something like float nan. Nan is not equal to anything. It represents an error type. So it's identical to itself, but not equal to anything. Equivalence does not imply identical. Identical does not imply equivalent. They're two separate characteristics. One interesting thing that you might notice is up to a name binding, equivalence is a transient property, whereas identity is a permanent property. What I mean by this is if at some point in time X is Y, unless there is a name binding, unless there's a line of code that says Y equals something somewhere here, X is Y forever after. The only thing that can change X is Y from being true to false is a name binding. However, if X equals Y, many, many things can change. Whether X equals Y, any operation to mutate this data, if this is mutable data, can change this. If this is immutable data, then the only thing that can change this property is a name binding. But in general, for immutable and mutable data, equivalence is more of a transitory property, whereas identity is a permanent property. Now, let's talk about imports and import styles. Different ways for me to import things. I can say import math, math.sign. I can say from math import sign. And the decision between which I might use may come down to how much typing I want to do. Do I want to write math.sign a bunch of times, or do I want to sign a bunch of times? And you can think the number of times you write this element and the number of times you write this element might give you a sense of where the bulk of the typing is. Of course, you can always do the aliased import like this to reduce that typing to a marginal 2 characters, the single letter name of the module and a dot. But largely, you can see the distinction here is not that major. I mean, are you really losing or gaining that much time typing one or the other? I don't know. You can also do from math import star, which has the benefits of the m.sign, which allows you to say, okay, now I want to use cosine without having to scroll all the way up to the top of your program and add another entry to the import. Whereas here, you could say from math import star, and you could use anything that came from that math module without having to explicitly import it, without having to have the extra typing. However, one thing we know about Python is if we're reading through some long Python code and we see a function, we can figure out where that function came from. And we can figure out where that function came from in a couple of different ways. because this has some runtime existence, we can say, f equals and look at it. We can say from inspect import get file, and we can ask Python what file this function was defined in. But what we can also do, more or less, there's some contortions that allow us not to do this, but what we can also do is we can statically identify where this function came from, because the only way a name can be bound in Python, a name can come into scope, is via a finite set of strict syntactical forms. If you see X somewhere in your program, it must have come into being either by an import X or a from something import X, or an X equals, or a for X something, or an X with an assignment expression, or an as X, or an except as X, or a class X, or a def X, or a couple of other formats. The case statement adds a couple more, or the match statement adds a couple more. But there's a finite limited set of strict static syntax that creates a name, creates a variable. And you can just scroll up to see, how did this variable come into being in my current scope? And you'll succeed at that. What that means is, if you do an import star, well, how do you know which of these two modules this came from? If I say from math import star and from logging import star, and I do log of 1, is this math.log or logging.log? Because they don't do the same thing. This is why we generally guide people not to use import star, because you lose the ability to statically trace where did something come from. And people generally do not expect that reordering imports will change the behavior of the program. Here, the program is correct. This is math.log, the latter one wins, and you can take the log of 1. Whereas if we sorted our imports in reverse alphabetical order, this program is now wrong. This is logging.log. So generally, we avoid import star pretty much any circumstance we can. I can only think of 3 places where you might ever use import star. One alternative to either of those import is maybe an alias import on the name itself. So this is another way we could distinguish between this is the level bug. Here, you can see we can import math.log as logarithm or logging.log as log message. And this is basically just doing this. Import math, logarithm equals math.log. And similarly, and so we can rename these things to our content to eliminate that potential ambiguity in our code. Well, one thing that I often do is I'll often use these alias imports to eliminate that ambiguity deep in my code. And you've seen me do this quite a bit, especially when a name overrides one of the built-in names. Who knows if somebody wants to use compile later? I don't want them to be confused if it's the regular expression compile or the compile. Or I'm using JSON and pickle, and I'm using the load S and the dump S for both of those because I like my from whatever import syntax. I might alias these imports. But I want to talk about what the difference is between these imports in terms of what they might do to your code. Here, from math import sign is basically saying import math, sign equals math.sign, del math. One important note is that the import statement in Python does not execute code. Dead stop. Import is not about executing code. It's about making something available to use, where the side effect of that might be the execution of code. Let me show you what I mean. When you say from math, import cosine, sine, and pi, what you're actually doing is an early binding. You're doing a snapshot view of what cosine, sine, and pi are as of this line of code. And so you're saying, go into the math module, get cosine, sine, and pi, fix myself to whatever those are. I'm going to early bind to those. I'm going to take a snapshot. I shouldn't say snapshot view. I'm going to take a snapshot of these, snapshot copy. If somebody tried to play a joke on you and they went into the math module and they mutated the math module, which is a completely fair thing to do, maybe not mutating the math module, but mutating modules is a fair thing to do, and they reversed sine and cosine and they made math.pi equal to 4, you would not see that change because you took your snapshot all the way up here. And so any subsequent changes, this horrible joke your coworker is trying to play on you, you will not see the consequence of. What you can think is this import style is an early binding. It gets what the value of it is right then and there, and then says, you know what, I don't need to get updates to this. That's not necessary. I don't expect there to be updates that are going to be relevant to me. Whereas when you do import math and then math.sign and math.pi, you're actually looking up what the sine, the pi, the cosine are live. This is a live view, which means if somebody went into this module and they changed things around, you will see those changes. In general, there may be circumstances where you need to be responsive to changes of pieces of the standard library. For example, sys.breakpoint hook, you assign to it. You need to look at the sys.breakpoint hook somewhere in your code. You might need to do a sys.breakpoint hook to explicitly get what the live value, because you can't guarantee that whatever early bound version you have, that snapshot you have, is still a valid snapshot. This is why when you look at things like the sys module often has getters and setters. It has get profile, or I think it's like get trace, and set trace, because this way they make it really clear that you're getting the live value, because otherwise you'd see that people might say from sys import trace, or other people might do import sys.trace, and they might not recognize that this is a snapshot and this is a live view. This is early bound and this is late bound. And so sometimes these modules do this. You see things like locale, get locale, where they don't necessarily have to do it because Python can retain this distinction versus the order of the bindings. Let's talk about what happens when you import a module, because it is oftentimes mistakenly believed that this is more efficient than this. This only executes the code to give you trace, whereas this executes the whole module. That is not what happens when you import a module in Python. Because when you have some code in a Python module, it needs to be evaluated to create the things that it contains, the functions, the classes, and whatnot. If this function relies on another function in its global scope, how does the Python compiler, or how does the Python interpreter know that it only needs to implement this, not implement this, without having to read through this code? And remember, this could be arbitrarily complex. This could be like a globals. This could be a choice of FGH. No, actually, G and H is a little safer. Nope, actually, this should be safe because we could do a globals here. We could do this. We could make this arbitrarily obscured to the Python to anything but the Python runtime. And how does it know which of those it needs and those dependencies? It doesn't. So you know what Python's going to do? When it executes a module, it's going to execute everything because it has no idea what it needs, and it has no ability to statically trace. Oh, F relies on this, relies on this, relies on this. There's no possible way for it to see through this complexity. Also, you can do something like this, and it's completely valid in Python. K equals H. How does Python know if you want to say import, from module import K, what K is, unless it's evaluated everything leading up to this? And because module bodies can include arbitrary code, like stuff that requires non-determinism, requires access to or knowledge of the state of the random number generator, or even access to user inputs, Python cannot do anything but execute the module in full. Anytime a module in Python is evaluated, it is evaluated to completion from top to bottom. Every single piece is evaluated in it. Obviously, the function bodies aren't evaluated. It's not going to call the functions until you actually invoke them. But every piece of executable code at that top level will be evaluated. You cannot partially evaluate modules. You cannot partially load modules. That's not strictly correct because there are certain parallel implementations of Python, but they're internal specific. Some of the big tech companies have their own internal versions of Python which allow for partial module execution. But generally, CPython, the one that you and I use every day, and even those are very restrictive on anything like partial evaluation. In general, you can't really make use of that. The import styles do not vary in that way. Critically, also, the import statement is not about running code, because no matter how you write that import statement, the entire module will be evaluated. The import statement is about making a name available for you to use. The from whatever, import whatever is about making that name available to use right then and there with the snapshot. Import module, module.f, making one name, the module name available for you to use, and then dynamically at runtime looking up the pieces that you want. Here's how module execution, module import more or less works. And I've done this by mocking up the import statement. When I say import mod, it basically runs the built-in function import, which has a lot of mechanism behind it, but this is the simplest version of it. It'll look through your sys.path, and it'll look for a file named whatever.py in your sys.path. When it sees that file, it'll parse that file to generate an abstract syntax tree. It'll compile that into bytecode. It'll execute that bytecode. It'll create a new module. It'll take everything in the namespace that it executed, copy it into the module, and return it. Here is a very simplistic view of how module import actually works. step by step, ignoring a lot of major details. There's, how do we actually find this? There's sys.metapath, there's sys.path hooks, there's, things like the zip file import and all of those mechanisms. But this is the historical, bare bones, single.py file import mechanism and how it works. What you can see here is exec is undeniable in Python. Module import uses exec, and what you can see here is the module is read as a whole and executed as a whole, and then presented to you for use. The import statement does not actually import this module because one step that, I don't know if it goes in import or not, but one step that I should add to this is there is a cache for imported modules, not modules. And the very first step is actually looking if this has already been imported before, burn it. Because in a Python program, you never really know where your code might run. If you say import module, unless you control the entire program, this program has multiple files, multiple entry points. You never really know, is this the very first time this module is imported? Could have been imported already, and you could be getting the cached version or not. Because you don't know if your import is the one that's going to execute the body, or if your import came after somebody else who executed the body, you can't really make use of anything happening at module scope and the timing of anything happening at module scope to implement some business. Instead, what you can do at module scope is you can say, if I'm going to import a module, the module would have been executed to completion in its entirety at some point prior to this import statement. The import statement as a side effect executes the module, makes it available for me to use, but I can't really have fine-grained control of the timing because I don't really know what that timing is. This module could have been imported by things which are outside of your script, like your site setup. When you do the capital S to turn off your site stuff. There's all sorts of .pth files and whatnot that can incidentally import this module, and you might not know that you were actually the second person to import it, and thus not the person to execute. Our conclusion from this is there's a firm distinction between snapshots and live views. Early binding means snapshot, late binding means live view. The import statement does not actually execute code, and Python modules cannot be evaluated partially. They must be evaluated to completion.